Hi everyone, my name is Antal. I'm a senior quantum software developer at Xanadu, and in this video, I would like us to have a look at how certain expectation values can be represented with Fourier series. This representation is very important in order to derive some general parameter shift rules that are used in order to compute quantum gradients. If the notion of computing quantum gradients is new to you, I encourage you to check out our video on how quantum gradients can be computed on hardware. In addition to quantum gradients, this Fourier representation is also useful in order to consider what the expressivity of certain quantum models can be. You can find links to relevant research papers in the video description below. All right, let's start with some notations and introduce some definitions. First, let's introduce the expectation value of an operator B. We can write it up as a function Ex, taking a single scalar input, such that the expectation value is this expression. We are computing the expectation value of operator B such that we have a quantum state psi, which is evolved by some unitary Ux. We can further write Ux as e to the power of Ix where G is going to be the Hermitian operator.
Hey, Isaac here. If an operator can be written in this form, G is called its generator. To see what the generator of an operator is, you can use qml.generator. So for this example, the generator of a y rotation gate is simply the poly y gate with a factor of -1/2. In the notation we're using in this video, that just simply means that G is equal to -1/2 times poly y. Back to Antal.
The eigenvalues of G we can denote by some omega j values. We will create a set out of these eigenvalues such that the eigenvalues are ordered in a non-descending order, and we will write that J is going to be from a square bracket D set such that this square bracket D set is going to be defined as the set of positive integers going from 1 to D. Further to that, we can also introduce the eigenvalues and the eigenstates of Ux. The eigenvalues are going to be e to the power of Ix omega j, such that j is from this square bracket D set, whereas the eigenstates can be noted as some phi j cat, such that once again j is from D. Also noting that phi j cat is going to be the eigenstate corresponding to eigenvalue e to the power of Ix omega j. At this point, we will introduce two more definitions, one of which is going to be psi j, which is going to be defined as bra phi j, psi j, cat psi j, and also bjk, such that this is going to be equal to phi j, bra phi j, cat phi k, such that j and k are from this square bracket D set. Once we have these notations and definitions in place, we can re-express this expectation value by expanding each of these terms in the multiplication in the eigenbasis of the unitary Ux. Let's have a look at what that will look like. So the expectation value Ex can then be written as a sum, such that we have two indices j and k going from 1 to D, and we will have a component for each of the terms out of this vector matrix multiplication. So we will have the component psi j conjugated. We will have e to the power of Ix omega j, this whole expression conjugated, bjk, e to the power of Ix omega k, and psi k. Based on the definitions of psi j and bjk, we can convince ourselves that these two equations are equivalent. All right, once we have this expression, we can further expand on it by considering which terms in this product are x independent, so they don't have any x in their expressions, and which terms are x dependent. Let's write up the same expectation value based on this criterion. What we can write is we will have a sum where we have a single index, j going from 1 to d, such that we consider j equals k. And if j equals k, what we have is psi j conjugate times psi j, which is going to be the magnitude of the psi j component squared times bjj. And if we have a look at the x-dependent terms, they will cancel out because we have omega j here minus omega j here because of the conjugation. So we have the j is smaller than k and j is bigger than k elements left. What we will do is we will create another sum such that we have j is smaller than k. We'll see that this can be useful to write up the j is bigger than k elements as well. But first, we simply just write what we had up there with the reordered terms. So we will have psi j conjugate times bjk times psi k, and we have the x-dependent term, which is going to be e to the power of ix times omega k minus omega j, where we have performed the conjugation from there. So as mentioned, we've just written up the j is smaller than k terms from the sum here. We have also written up the j is equal to k terms. What remain are the j is bigger than k terms. So we will have a sum here within the sum. And in order to write up the j bigger than k terms, we can just swap the role of j and k in the original expression and reorder the terms in the product slightly. What we will have is going to be psi j, bj k conjugate. We can write this because of hermeticity. Psi k conjugate e to the power of ix omega k minus omega j. This exponentiation is conjugated, and this is going to be the second summed in this summation. So once again, what we've done here is that we have reordered these terms that are being summed based on their x-dependence. Okay, so we have seen how the expectation value of an operator can be expressed such that we are grouping up the x-independent terms and the x-dependent terms in our sums. Our next step here is going to be introducing the concept of positive unique differences. What we've seen is that in the x-dependent terms of the expectation value, there will be such differences in the exponents, omega k minus omega j, such that j and k are from square bracket d, and omega k is going to be bigger than omega j. If we create the set of such differences, we will call this set the set of positive unique differences. Let's denote this set by creating an uppercase omega L values such that L is from the square bracket R set.
You can actually calculate sets of positive unique differences like this in PennyLane by using a method in the Fourier module called getSpectrum. Just give it your operator and it returns the set of positive unique differences. 0 is also included in this set, but it can be easily removed.
At this point, take a note of the magnitude of D. D, let's remind ourselves, was the number of eigenvalues that the generator G had. So G has D eigenvalues. Well, if our unitary Ux, which G generates, acts on n qubits, Ux acts on, then D is going to be equal to 2 to the power of n. So we will have exponentially many eigenvalues for this generator. However, if we are lucky and this Ux has degenerate eigenvalues, so some of the eigenvalues appear more than once, as well as if these differences appear more than once, then what we could have is that this D is going to be bigger or way bigger than the number of positive unique differences appearing in this set. In such cases, we will have a simplified form for the expectation value, as we will see in a bit. You might ask yourself, okay, how could we write up these positive unique differences for a special or like a specific operator? So let's have an example. Let's consider some O, that is an operator whose matrix is going to be diagonal, with matrix elements of diagonal elements being 0, except for the diagonal where we have 1, 2, 3, 4 in the diagonal. What we can convince ourselves of is that omega 1 is going to be 1, omega 2 is going to be 2, omega 3 is going to be 3, omega 4 is going to be 4. In order to create the positive unique differences using these lowercase omegas, what we can do is first fix the smaller eigenvalue being 1 for the smallest one, and then consider the other eigenvalues, such that we will always have omega k being bigger than omega j. We have omega j here as omega 1. All right, so we have 1. Which eigenvalues are bigger than 1? Well, we have 2, 3, and 4 bigger eigenvalues than 1. So we will have 2 minus 1, 3 minus 1, 4 minus 1 equals 1, equals 2, equals 3. So these are the positive differences for when the smaller eigenvalue is 2. What are the positive differences when the next small eigenvalue is going to be 2? Well, we have 2 eigenvalues which are bigger than 2, 3 and 4. So we will have 2 differences, 3 minus 2 equals 1, and 4 minus 2, which is equal to 2. So we have these 2 differences when the small eigenvalue is 2. We have a last pair where we will have omega 4 minus omega 3, such that we have 4 minus 3, producing the last difference, which is going to be 1. Well, these are then the differences that we have considered, the positive differences of the eigenvalues, but the set of positive unique differences is going to be the set of 1, 2, and 3, because some of the positive differences appeared more than once. So this is going to be the set of omega L, uppercase omega L, where L is going to be taken from, once again, this square bracket R set. And for this specific example, we will have R equals 3. Okay, we have seen how we can use the concept of positive unique differences for a simple operator. Let's also see what type of definition we can use in order to simplify the non-x-dependent terms. In specific, let's introduce some CJK coefficients such that this is going to be equal to psi j conjugate bjk psi k. Such terms appeared in the expectation value that we have written up recently. If we have such coefficients, and we consider once again the positive unique differences, which were these uppercase omega L terms in a set, what we can assume is that there is going to be a mapping between such L indices. We will be referring to these indices as frequency indices because they will be determining the frequency of the Fourier series that we later obtain. So there will be a mapping between these L frequency indices and the JK indices that we have from before. If we assume these, what we can then do is rewrite the expectation value that we previously had such that it is going to be equal to some A0, where let's write A0 as the term that we had for the j equals k elements. So it was the sum where we had the sum j equals 1 going to d. We had the magnitude squared for psi j, and we had bjj. So let's have this as the a0 the a0 term in this sum, and write up the next term using the frequency indices such that L is going to be going from 1 to R. We have a coefficient CL. We have the exponentiation term e to the power of ix omega L plus the remaining terms which have conjugated coefficients as well as a conjugation basically in the exponentiation term. So we will have another sum L equals 1 to R CL conjugate e to the power of minus ix omega L. Once again, we've rewritten the previously derived expectation value formula by using these frequency indices where we assumed that there was a mapping between such frequency indices and such JK indices that we've used before. The coefficients CL will then be containing each of the JK terms and could be expressed using such CJK terms and using this mapping between L and JK. At this point, to derive the last bit of the Fourier series representation, there will be two components required. First, we will be switching from the CL coefficients to some AL and BL coefficients, as well as switching from the exponentiation terms to some trigonometric expressions. For the first one, let's introduce the two new coefficients that we would like to use, such that CL is going to be 1 over 2 AL minus I BL for every L out of square bracket R. All right, let's complete the definitions of AL and BL by also mentioning that these coefficients are going to be real numbers, and also mentioning that the previously defined A0 coefficient is going to be a real number as well. Once we have these three types of coefficients, let's also just note once again that the exponentiation terms in this sum can be rewritten as a trigonometric, in terms of trigonometric functions by using Euler's formula, allowing us to rewrite the expectation value Ex such that it is going to be a sum A0 plus summation where we have L going from 1 to R, sum AL times cosine omega L x plus BL times sine omega L EX. If we have a look at this expression, this is a cosine sine form of a Fourier series.
A really cool fact about this expression is that we can now evaluate such an expectation value, which was originally a measurement on a quantum circuit, as a classical function. Let's take this simple circuit for example. In PennyLane, the Fourier series representation of a circuit outputting an expectation value can be calculated under the hood via qml.fourier.reconstruct. We give it the circuit and this parameter called num's frequency, which is basically a dictionary whose only key in this case is a parameter name, x, and whose value is another dictionary whose key is an empty list and whose value is 1, indicating that x is a scalar, and we only need one positive unique difference to evaluate the Fourier series representation. There will be some number of times that we need to evaluate the quantum circuit in order to perform the Fourier reconstruction, which we can see via dev.num executions, which keeps a running tally of how many quantum evaluations the device has performed since it was created. However, once we have created the reconstructed form of the circuit and we call it many times after that, we accrue no extra quantum evaluations, meaning that we've evaluated this expectation value classically.
So what we've done here is we've written the expectation value EX as a Fourier series, where this Fourier series will have finite terms. The cool thing about this is that in order to determine these AL and BL coefficients, we can evaluate the expectation value EX finite number of times, and through discrete Fourier transform, we can determine these coefficients. Thank you so much for tuning in and looking at this video content today. See you in the next one.